So today I'm just going to talk a little bit about the encoders that I did actually try on the M1 and eventually the one that I settled on, and I'll talk a bit more detail about that. So the first encoder that I did actually try was this CUI encoder, which is basically the same one that's recommended on any of the O drives and stuff that they use. Some of the limitations of this encoder though are that it's only incremental and it doesn't actually have that higher resolution. So initially I did try it on this system, so this was the very first prototype that I did 3D print and build. You can see a little bit on the inside there. And it was designed so that this encoder could fit on the mounting bracket that goes on top of the main end effector. So you can see that does just clips in there. But one of the big limitations, especially of using this encoder, is because it's quite big and bulky. I have to mount this PCB off the main end effector. So this is where you'd have the motor sitting, but yeah, so this has to sit off the back and it makes the entire system really quite big. And I'll talk about that a little bit towards the end. So anyway, I tried this one first, wasn't great. And then actually watching James on YouTube, that's when I came across these little guys. I think in his video he was using I2C encoders, but this one here is an SBI encoder by AMS. And this is actually a magnetic encoder. So one of the really cool things about this one is it has a relatively high resolution. I think it's about 14 bits. So you can get quite fine detail with using one of these encoders. But one of the actual drawbacks of using this encoder in particular is that it has to be placed by a machine, and there's not an edge that you can indicate off so that you know when you're placing it on the motherboard for the M1, you know it's in the exact right position. So that was one of the issues with this one, aside from the fact that the resolution still wasn't high enough. So moving on, doing a bit more research, I did actually find this other encoder by Broadcom, which is the AEAT 88000. So this one is, I think it's basically the highest resolution you can get for a magnetic encoder before you start moving to a lot more fancy ones that cost in the hundreds of dollars. So this little encoder here is 16-bit. So I think that roughly gives a resolution of 0.005 degrees, which is very, very high. Ideally, we'd like to have it higher, but we have to pay a lot more money to get a massive encoder that would do that. And obviously it doesn't have the same package size that this one does. And one of the actual major benefits of using this encoder is that it's actually a square package and it's very, very accurate. So this is a 5 by 5 millimeter square package. And you can see that I've actually used part of the design from this one. So I did actually try build an M1 motherboard with this one, but obviously, yeah, it wasn't accurate enough and I wanted that precision of this encoder, but I have used these mounting holes. So this is something that they did use in their sort of development board, is they have an encoder, a magnet that you can spin on top of this and it mounts into these 4 mounting holes. So I wanted to incorporate that into my final motherboard. But one of the main advantages of this one is that by having these 4 holes, we can actually use that for alignment, and because it's a 5 by 5 millimeter very accurate square, we can place the chip on the board very accurately so that we know when we try and align this with the encoder shaft, it's going to be basically spot on. So I'll get the other parts and then I'll show you how this one works. Alright, so essentially when I'm actually trying to mount these encoders on the board, there's basically three parts. I've got this, which is the jig, and you can actually see in there we've got the 4 mounting holes that can go into the board, and we've actually got a very accurately machined recess here, the square. It's 5 by 5. So the way this works is we can take a chip. We've got a couple here. So we've got one chip. Basically the way this works is you can see I've put a tiny little index there. If I take this bad boy and mount it in the jig, you can see it seats in there pretty accurately. And then this is a board that hasn't had the encoder applied. And one thing I forgot to mention was the main reason having a jig that we can really accurately mount the encoder on is that we don't have to worry about doing two-sided SMT. So with this system, we can do all the SMT on the top side. There are a couple of components missing. We can do all the SMT for the top side and then do this very accurate placement of the encoder offline, so it doesn't have to be done on the machine. So anyway, the way this would work is you'd apply your paste on here using your stencil, and then taking the jig, we can, obviously making sure it's aligned properly, can go like that. Then we have this little guy, basically just a little pokey rod, and that just goes down to apply a little bit of weight on the chip so that it comes off, and then we lift up. You can see that that chip is placed right in the middle there, and it's quite accurate. So anyway, so that's the general idea behind using those 4 holes and that encoder. Right, so I did briefly mention before that when I was using this CUI encoder, you can see that this system all up takes up quite a lot of space, because you can't actually mount the motherboard on top of where the encoder is sensing, so it has to be mounted at the back, and that obviously takes up a lot of space in the system. So basically this is the very first prototype that I built, and it was just because I didn't really know much about encoders at the time, so I figured if I used the CUI encoder that gets used by a lot of the O drive servos that I've seen people building, maybe it would work. And I didn't do the research at the time. So anyway, I tried that one, and then this was actually the enclosure that whole system was mounted in. And you can see it's quite bulky. So this is the work area. So it basically has a radius that it can do all the placement and stuff in, which is only 250 mil. But for 250 mil, you actually need 610 millimeters of machine. So there's a lot of dead space on either side of the working area that gets wasted with this system, because you're taking up a lot of space using the PCB. And if we compare that to one of my final designs, which is this, so this is an M1 400. So that basically means that this machine has a 400 millimeter work envelope. So you can see on this one, for 250 mil here, you need 610 mil, and on this one we've actually got 400 millimeters of work envelope, but the machine is still only 605, or basically 600 millimeters long. So for the exact same size machine, we're getting an extra 150 millimeters of all work envelope on the final design of the M1. And this basically comes down to the fact that we can mount this PCB right on top of where the work is being done. So on here, this is where the encoder sits, and spinning that goes straight through this board up to where this encoder actually sits, and we can actually mount that right there, as opposed to obviously with this design it would have had to be mounted like right down here or something like that, and it's just a lot of wasted space that you obviously want to try and gain back to make it a little bit more easy to use and ergonomical. So yeah, so that's basically the 3 different types of encoders that I did try when I was building the M1 and the final one that I settled on. Obviously, all the links and stuff for the encoders that I did use, I'll try and put that in the description. And if you want a bit more of a detailed breakdown, it's probably a good source of information is that Hackaday, not Hackaday, is it Hackaday? Yeah, I think it's the Hackaday IO. So that's where I'll be posting more detailed information, so where you can find these encoders and the different code that I was running to get all of them to work. So in the next video, I'll probably just be talking more about the mechanics of this M1. So I'll be taking the cover off and I'll give you a closer look on the inside of how it actually works. Anyway, thanks guys. Obviously, if you got any questions or things that wasn't clear, let me know and I'll try and do my best to fill you in the next video. Thanks.